macro and all that.
Yeah.
So we have a current scenario of that. So how do we get in touch, or how do we?
You can actually
This is a power distribution,
GitHub,
which is like
repository of
this gives a lot of power. This you see one line is coming.
It's a case study which we can.
So it distributes the power.
You can give me one of the number cards.
We have a card. Number.
You can take my number.
Sure.
70544
205
7041 414.
70544
7041 70544 70414. This is regarding you.
So we have a scenario where we are currently looking at transmission.
You can say my name is Rahul. I can get your name.
Aman. Aman. PhD student.
Where we final year or
Like pre-final.
We'll share the requirement. So basically, we have an electric vehicle requirement wherein we believe that we require a gearbox. We are testing at the moment with a 6-speed standard, like a two-wheeler gearbox. What we want to come down to maybe is 3 ratios, which gives us the right balance of torque and top speed. With a smaller motor, we are looking at a 4.5 kilowatt.
So this is the trajectory that it will execute for these initial conditions. So now let me add another system. So this was our initial for these initial conditions. This was our trajectory. So anyone wants to try matching these initial points? Here, come try. Yeah.
Give us that black tape. No, black tape.
This bob. Yeah, anyone try. That's all. You're not close. You have to try.
Do something here.
Okay. Well, okay. So that is really good. So now you can try playing. So initially you will have an almost perfect tracking of our blue trajectory. But then with time, you will actually see that it slowly deviates. So as you can see here, you can see a separation between our blue and red trajectory. And then with time, it will slowly increase. The deviation will increase to such a point that it has a completely different trajectory. So this is what we call as a deterministic chaotic system. So if our initial conditions are not exactly the same, you will have a completely different trajectory. Yes. So that is what we have as a double pendulum system. So double pendulum systems are one of the most basic systems that are used to study nonlinear dynamics. So you have linear dynamics and nonlinear dynamics. So most of your world is modeled by this form of nonlinear dynamics. So our control strategies that we use to control other systems, let's say for example, or any other, has some are controlled by nonlinear dynamics. So our control strategies can be used for this for this double pendulum system, and then they can be used to benchmark our control strategies. So yeah, so that is one of the most widely used cases of a double pendulum system, is to study other bigger nonlinear systems. That's all we have here.
Is it made using plasma?
yeah.
Python system.
Yeah, this we are using Python program. Yes, so this simulation is the
Scratch, no?
huh?
Python.
Yeah, this is Python. Yeah. So this behind it's a completely Python program that we wrote. So this
That's working.
yeah. So what happens is this is a arithmetic representation. So I can
Now the problem is what quantity in this matrix can help us in convergence determine. So that comes from eigenvalues. So if you look closely, this matrix will always have one zero eigenvalue. This matrix will always have a zero eigenvalue, and other eigenvalues will always be non-negative. So the second eigenvalue which you will have, that will determine the convergence speed. And if that eigenvalue is small, then agents will converge very slowly. And if it is high, then it will converge. So eigenvalues basically depend on the connectivity of the agents. So we have simulated some scenarios. So we are trying to show you some
basically the idea will be to show how this matrix, the design of this matrix or this adjacency matrix will tell you about how fast the consensus happens, where things go. So we'll have a lot of agents in this 2D coordinate. This is just a simplified person code simulation, where at the end they will all converge to the same place.
So first we will show you some scenarios and then we have some game in which you need to guess the number of
This is how the
clusters
consensus
or
happens. You start with a random graph,
Okay,
all the agents are at different locations. As the simulation goes on, they will all start converging at the same point. And I mean, definitely the simulation will go on, the error will start reducing. And those are the eigenvalues.
Yeah, so this is sparse random. That means not all agents are connected fully. Some are just left alone. So that is like, you can see the eigenvalues look like this. One is 0, others, the second one will determine the convergence rate. But if it was fully connected, then this eigenvalue will be very high. So, and this is the, yeah. You can show scenario 4 me.
Scenario 4, right? Actually, this is dense.
No, this is noise. So what it is happening is in this scenario, each agent is not reporting its own position but some noisy estimate of its position. So then we want to find if the convergence will still happen or not, if the information is not correct. So the consensus still happens, it says that the position is jittering, it will keep on oscillating.
No, we can go with that cluster one. So, I can intuitively tell you what is happening. So, when all the agents are at some random position, if you pick one node, they are connected with some of its neighbors, right? And in the next time iteration, they will have to move closer. Now, where will a particular node move? That one node moves to the median of wherever, suppose it is connected to 4 nodes, so there is one centroid location, it will try to move towards that. It is average of all the neighbors to which it is connected. So ultimately what will happen is that suppose it will start at certain position, there is some significant, and the next time iteration that distance becomes there. And again in that iteration it will
I think this is just in a scale
it will try to
whether we have scale just whether one
I think it is not like within control.
With that also.
So this is what this gearbox looks from the inside. It is a planetary gearbox. There are 3 planet gears here, and there is 1 ring gear on the outside. Right? So the motor has a sun gear. So this rotates, and the output is basically the magnified torque count. This is just a power distribution board. Takes in the battery and it connects both of them. This is a motor driver. This pushes current through the coils and it creates a magnetic field inside the motor. And because there are magnets on the outside, because of the magnetic field, the output
మన
rotates.
ఇంట్లో యూజ్ చేసే చిన్న ఇది గజి మోడలే కదా
So usually for robots there is oral motor driver. For example, if I tell like a small robot will lift something,
Huh.
you have to convert that into a signal and then lift it, right?
Yeah.
So you convert that through this part.
Yes. So basically using using a code on my laptop, I am telling this to rotate in a specific way. So that signal is converted into motion by this motor. So each of these are used in joints like 1, 2, and 3. So, but
Because of this high pressure of this one, so we need to apply more pressure.
no. The thing is, each joint will have an actuator. You think of it like each joint will have an actuator. The higher the amount you are taking, the higher force you are applying, the force of the motor gets multiplied by each. So let's say this increases the force by 10. This increases the force by 10 more. Then the overall force increases by 10 into 10, 100 times. So if it gives a force 1 Newton of force, this will give you 100 Newton of force. You end up using a much smaller
Here only.
Yeah, so you have to just so this is a driver which tells the motor how much force to put. Same as this. So this also has a driver which is connected to the computer. So this computer is telling, okay, apply this much force or this much something, and this is giving appropriate amount of current, and this is rotating. And about the torque.
So unidirectional we can control.
Yeah,
How many steps we can rotate, that also we can control.
Yeah, you can control. So there are several modes of control. Let's say in humans, how do you say you have to lift a weight? So you think about, okay, I have to apply some force. You don't care about how fast I have to move. Then let's say you are playing badminton. You care about how fast you have to move. Same thing you can do in this. If you want to run it in force mode, you tell it this is amount of force I want. I don't care about how fast I move. If you want to move it in fast mode, like velocity mode, in which you care about how fast my hands move rather than how much force I apply, so you can run it in velocity mode also. So you give a velocity, it will run in that. It doesn't care about the force. So it can work in all those. You have to in all different modes. To rotate that, we are using this.
Yeah.
So this is a motor rotates. Right? A motor does not have enough force to handle this big.
So these are one of the two use cases that can be. Yeah, so that is pretty much all we have for the double pendulum system. Yes, thank you. Hi.
Can you explain?
Yeah, so this is a double pendulum system. So have you heard of a pendulum, single pendulum? So where do you think we use
Swing.
a swing? Okay, a swing is a very good example that I haven't heard. But yes, so how do you think a single pendulum system moves or works? Have you seen the motion of a single pendulum?
Yeah.
So how is it?
We start from a point and end point in the same direction.
In the same direction. So that is what we call as a periodic systems. Yeah, periodic motion. So a double pendulum system is just a single pendulum system, but then with two links. So here you don't see one link, you see two different links. So this is what we call, so this becomes a chaotic system, a double pendulum system, but specifically it becomes a deterministic chaotic system. So it does have like a mathematical equation behind how it moves, just like your single pendulum system. But then if your initial conditions aren't exactly the same, you will have a completely different trajectory. So this is a simulation that can exactly show you what a deterministic chaotic system is. You can try placing the try using the simulation.
She only kept.
It is not just this would be
We capture into a matrix we call it adjacency.
what this adjacency matrix tells you is that suppose this is the row 1 is the robot 1. If there is a 1, it means that the robot 1 can communicate to robot 2. It can communicate to
Robots.
cannot communicate. This matrix simply tells you how to That is actually a very good But then you see with time, you have more separation. It's getting a little wider. It's not exactly your trajectory, but it's here we have so this is what is known as a deterministic chaos. If your initial conditions aren't like exactly the same, you will have
Yeah, we are doing that. This is not.
and is this like what are you build?
This is we got. We have a custom driver, but it's a very big.
So I want a BLDC motor for building this reactional patient. Buy one. So I don't want gears and all. Because I just keep
Just buy the motor. Bring gears. So it might not. This is an O-drive Pro motor. It's off the shelf. Motor also you'll get off the shelf. I feel fast. Motors are fast enough. If you walk, so the motor is like it has very less torque, but it has very fast RPM.
Okay. That's what we are doing.
Yeah. So if you want high RPM, use direct drive, like no gear.
So, but still you need control, right?
Control is this. So this is like you don't have to do anything. So
We don't need FOC for this.
FOC is inbuilt. You just buy it off the shelf, and it has a very good like user interface. Just give you want to run in torque mode, set torque mode, and give the torque. Run in that torque. If you want to run in velocity control mode, give the velocity control mode, and then go right. If you want to run it in custom trajectory or something, it's like Python code.
So what is the load?
So there are different
we can get the patient's diagnosis by the gold standard, which is the doctor's diagnosis.
No, go ahead.
So I'm trying to reach community as close as possible, right? So here what we're using is we'll take spontaneous speech of the patient. One thing is that where, sometimes a depressed patient can sound low and an anxious or happy patient, talks really fast. Such things into consideration. We have validated 4 WHO questionnaires, which are currently being employed by the health workers in the community and by the doctors as well. So we take that, the scoring system from there, and we have the final doctor's consultation, which is considered the gold standard, right? We have a psychiatrist consultation. All 3 combined together, we will see if how much AI can come as close to the psychiatrist diagnosis, and we're trying to bring mental health being screened easily to the public, as accessible as possible, right? So if you want to try that, we can take it forward.
That their government is already using that. We are trying to make it in a large scale by putting it in different states like Ultrasound and all of that. So so that is basically so that they don't have to we use their brain and all of the Asha people and all. They can just take the picture and it will say, and they just have to refer them to the dentist immediately, so that from there the dentist can, or the surgeon whoever is there, can take up the cases. So at least if the treatment they can diagnose it earlier, the treatment is easier and better, and the survival rate also is better. Yeah, so that is the basic issue. If you want foods.
Covering not some table. So you have to agree to the terms and conditions of the app. And then you'll be asked questions about your age, background, and when they had their first menstrual cycle. Because all these things are lifestyle dependent. It depends on the lifestyle. So in urban cities, just imagine one girl would have been following a very nice lifestyle when she was in her house. All of a sudden she comes to a city like Bangalore or any other city. So her lifestyle changes and their food habits will change. So many things are a part of these non-communicable diseases.
ಇದರಲ್ಲಿ ಆದರೂ ಅವರು ಸ್ಟಾರ್ಟಿಂಗ್ ಮುಂಚೆ ಸರ್ ಕೆಳಗಡೆ ಹೋಗೋದು ಇಲ್ಲಿ ಒಂದೊಂದುವರೆಗೆ ಹೋಗಬೇಕು ಇಲ್ಲೇ ಮಾಡ್ತೀನಿ ಈ ರೂಮಲ್ಲಿದ್ದರೆ ಹೇಗಿದೆ
Is it thank you? Have you found the keys? Where are the keys? Where is the key? I'm not playing. He's not playing. How is it coming? The camera. How does it play?
Camera and then something comes there and then the camera is connected to
Yeah.
computer and then again it's connected to this.
Yes. This camera is detecting what you are doing. Okay. If you put your finger here and make it tap, it will make the it has some model. So it detects your tap and then sends to my laptop and it will place the sound. So it's detecting your gesture. Okay. Yeah, you have found this.
Thank you.
Yeah.
Do you want to play?
Slowly. Maybe another time. Just leave it slowly.
Next time. Start ready. Start it over again. Start.
Second activity. Yes, perfect.
Yeah, third activity. What was the third activity? You have that. No, jump it. Yeah, third one. Fourth activity. Yeah, do it in the class. From down to top.
Yeah.
Yes. Yes, you want to. Nice.
Yeah, you're the word.
Thank you. Yeah, thank you.
First person of woman.
ಸಿಗ್ತಾ ಇಲ್ಲ Transmission. ಇದಕ್ಕೆ ಆಮೇಲೆ ರೆಕಾರ್ಡಿಂಗ್ ಮಾಡ್ಕೊಂಡು ಪ್ಲೇ ಮಾಡಿಬಿಡೋಣ. ಅಲ್ಲಿ ಸ್ಟಾರ್ಟ್ ಮಾಡಿಬಿಡೋಣ. ರೆಕಾರ್ಡ್ ಮಾಡ್ಕೊಂಡು ಎಲ್ಲ ನೀಟಾಗಿ ಪ್ಲೇ ಮಾಡಿಬಿಡೋಣ. ಒಂದು ಅರ್ಧ ನಿಮಿಷ.
Come, I'll explain. Now take our big photos, okay? Like we are explaining. Come, Santosh, come here.
You want to do? Can I explain?
No, sorry.
You can explain to me.
So you can see, comes to our. So okay.
Sir, you want to place your sign, sir. We are giving 8 signs. You want to place exactly which sign comes where. We are mentioning the dot also.
She's saying this.
Your name? For which one? Which sign?
Sir, only for this leg.
Yes.
Only for this leg. Yeah.
So where we will be
Only in
providing
this
the
highways.
on high speed corridors we will be providing. Actually, we only one year.
Correct, I hope.
We will help.
Who told the answers? So you.
Sir, only at the blue dots.
Only at the blue dot.
Yeah.
There is no blue.
Yeah.
Okay, you have to explain to me what it is. Yeah, roundabout means what is?
It's like a U-turn but
Full U-turn. Full U-turn. Correct. So why it is in triangle shape?
Grab attention.
Then circle also there. Correct. Understand, right?
Circle.
Also rectangle also there.
Circle already
No, circle also will be visible, right? No, I understood. You talking about I understand.
I know English, but then
No problem.
Right.
So it's a triangle.
What is this?
Right?
Traffic information.
No, that is a roundabout. That is
What is
correct.
this?
We will already found it correct. Yeah, that's why it is a triangle. So you need to study the sign boards and all schools. Which standard you are? Right? So it is a warning sign. This roundabout is actually the warning. So people are going. So there is a structure is there on the road. It's some that is there. So it's in triangular shape. Circle means it is a compulsory you have to follow it. That's why circle sign. The rectangle will be there. So that is the information. If you see Bangalore or like Mysore and all, you have a sign called Mysore 20 km, Bangalore 20 km. That is the informative sign. Understood? That is the thing. So this is a warning sign. This is a mandatory sign. Mandatory is compulsory. So this can't be disturbed. Okay?
This is for railway track, is it?
Yes, sir.
Where is the 25 kilometer speed? If is too fast.
Okay.
Okay. Now you tell me.
Sir, one more.
One more
here.
Okay, December. Okay, this sign you have to find.
So this is junction. This is the school zone is there within 500 meters. We want to reduce the speed.
What is the school zone?
Yeah.
Oh, I didn't see this. Okay, then. So school.
The school zone is there. Before 100 meters, we want to mention there is a school zone. After the school zone, the speed will be automatically increases. And if you're coming from this direction, we want to information there will be a signal is there. Please reduce the speed.
So
We want to mention there is a signal. And this is pedestrian crossing. Before the the perimeter, we want to mention there is a pedestrian. And this signal board should be comes to this direction. This direction. Because if I travel from this direction, it should be visible to opposite direction. If I place it here, it should not be visible because if I park the bike here, the signal board is not visible. The signal board comes to this direction. This is the correct side.
Nice.
It's confusing. Okay, you find the same confusing.
No, even for transportation.
And also it will be helpful for explaining the which side.
But you don't explain.
Then they will go and see like if they went for any signals, they will check whether they are placing proper.
Find the name. It's here only. So this is the sign. You have to find it.
No, same one. That's the reason we are giving different legs.
No. Use this.
Use that one. Yeah. This is for this one. This is for this one.
I said that it could be confusing.
Replace. Two correct.
I'm gonna give some gift.
What is it?
ಬನ್ನಿ ಪ್ಲೇಸ್ ಮಾಡಿ ಏನಿಲ್ಲ ಸೈನೇಜ್ ಬೋರ್ಡ್ನ ಇಡಬೇಕು ಇಲ್ಲಿ ಇಷ್ಟು ಸೈನೇಜ್ ಬೋರ್ಡ್ಸ್ ಇದೆ ಯಾರು ಸ್ಪಾಟ್ ಇದೆ ಇಲ್ಲಿ ಕರೆಕ್ಟ್ ಆಗಿರೋ ಸೈನೇಜ್ ಬೋರ್ಡ್ನ ಇಡಬೇಕು ನೀವು ಹೋಗಿರ್ತೀರ ಜಂಕ್ಷನ್ ಗೊತ್ತಿರುತ್ತೆ ಯಾವ್ದಾದ್ರು ಕರೆಕ್ಟ್ ಏನು ಅಂತ ಯಾವ ಜಂಕ್ಷನ್ಗೆ ಹೋಗಿಲ್ವಾ ಸಿಗ್ನಲ್ಗೆ ನೀವು ಸಿಗ್ನಲ್ ಮನೇಲಿ ಹೋಗಿಲ್ವಾ ಯಾವುದು ಬಸ್ಸಲ್ಲಿ ಹೋಗಿಲ್ವಾ ಸಿಗ್ನಲ್ಗೆ ಸಿಗ್ನಲ್ ಹೋಗಿದ್ದೀರಲ್ವಾ ನೀವು ಎಲ್ಲಿಂದ ಬರೋ ಡೈಲಿ ಲಗ್ಗೆರೆ ಬಿಡ್ತು ಗೌರ್ಮೆಂಟ್ ಸಿಗ್ನಲ್ ಗೊತ್ತಿರಲ್ವಾ ಮತ್ತೆ ಇನ್ಯಾವ ಸಿಗ್ನಲ್ ಆಯ್ತು ಮಹಾಲಕ್ಷ್ಮಿ ಲೇಔಟ್ ಸಿಗ್ನಲ್ ಆಯ್ತಿಲ್ವಾ ಆರು ಇಲ್ಲಿ ಬ್ಲೂ ಕಲರ್ ಇದೆಯಲ್ಲ ಅದ್ರ ಮೇಲೆ ಈ ಥರ ಇಡ್ತಾ ಹೋಗ್ಬೇಕು ಇದು ತಪ್ಪು ನಾನು ಹೇಳ್ತಾ ಇರೋದು ಕರೆಕ್ಟ್ ಅನ್ಕೋಬಿಟ್ಟ ಈ ಥರ ಇಡ್ತಾ ಹೋಗ್ಬೇಕು ಡೈರೆಕ್ಟ್ This should become to this direction. This should become to this direction. There should be no standing of vehicles. This should be pedestrian done. This should be correct. This should be.
They should come from this side.
Yeah.
They can't.
ಇಲ್ಲಿ ಮಾರ್ಕ್ ಹಾಕಿದ್ದೀನಿಲ್ಲ ನೋಡಿ ಅದಕ್ಕೆ ಕನ್ಫ್ಯೂಸ್ ಆಗ್ಬಾರ್ದು ಜನಗಳಿಗೆ ಅಂತ ಮಾರ್ಕ್ ಹಾಕಿದ್ದೀನಿ ಹೆಂಗ್ ಬರುತ್ತೆ ಏನು ಅಂತ ಈಗ ನೋಡಿ ನೀವು ಈಗ ಬರ್ಬೇಕು ಅಂತ ಈಗ ನಾವು ಇಟ್ಸ್ ಕರೆಕ್ಟ್
Do we get anything for making? Do we get anything for these?
Only for the
Another one sign also.
Thank you.
Okay.
Come.
I'll give some sign for you. You want to place the sign? Two signs.
It cannot be there. What's this?
You got already chocolate, but I was not giving. I'll give some.
You told it's like a specially everything. Yeah, but this is nothing is priority.
Take your time.
You know the coffee pool?
So in computers, what is the most common floating point precision? Okay, so I think it's up to 15 decimals. So 15 decimals is it's very good. So we won't have a problem with that kind of approximations with this simple systems. But yes, that is a possible scenario. But then with 15 decimal points, we won't have that big of a difference. But then this change in path comes from our change in initial conditions, because our initial conditions is not 100% right. Because you, like when you placed it, you guys were satisfied. But then there'll be some 0.001 or 0.1. So that
direction will be along the resultant direction of all the edges. But suppose if I infuse 3 malicious agents, so 3 nodes means there are 3 vertices of a triangle, and then there is a median point, centroid point. And now you have the lines that join the vertex with the centroid. So there will be 3 agents which will not decide where they will move depending upon where the connectivity is, but they will decide it on the basis of that line that joins the vertex to the median. Now, can you guess which are those malicious agents by seeing their behavior or their movement?
Sure.
Okay. So first of all, I will show you a demonstration of that. Then I can explain how it is happening, and then you can guess. Suppose after it will reveal quickly, and then I'll explain. Yeah, so these are the 3 agents. We can say that this always moves along this direction, this always moves along this direction, and this always moves along this direction.
They don't have the connectivity extended.
Yeah, so they will not, their movement is not decided by these 3 guys. His movement is not decided by these edges, but this line. They will always move along this line. We call them malicious agents because ultimately the convergence will happen at the point that they have decided, not where other nodes are deciding to go. So they can hijack it like and take it to any other point. Now can you guess this consensus? Suppose if I run this delayed simulation. Now the answer will reveal after a lot of time. So you will have to guess what 3 malicious agents are there. You can guess the numbers from there.
Six.
6 for 9. For 4 is there, but others are not there.
4, 0.
And if you collide with something, then if you collide with something, then like some triangle or something, then it collects information about your positions, velocity, and this information is used for our winning or something.
So where do you practically use it when you have written a paper?
Yeah.
So for which thing you have written the paper?
Like in this stealthy kind of things, autonomous vehicles or something.
Okay.
Something. If there is a attack is happening in your
way.
In your way, then it is like not recognized there is an attack happening, or some external disturbance is happening.
So it detects the obstacles coming in its path.
Yeah.
And moves automatically.
Yeah. And this is a I like implement this in the form of this code, but it is not like in different fields, because it's like formation or whole thing is like generated for a generalized kind of thing, not for specific this code. This power system is also used. There is this kind of attack is also happening, like voltage drop or it's unpredictable.
So by that you see there is a problem. Deterministic and chaotic are used to describe the same system. So what we mean by deterministic chaotic system is that if your initial conditions they are not like the same, you will have a completely different trajectory. Yes. So you can try. So here we have this red pendulum. You can try matching the initial conditions with the mouse.
Where is this applied in the real time?
Okay. So
Little that side.
huh?
Little that.
Little this side. Can you guys come this side?
Oh, sure.
Yeah. So where this is used, so this is a simple example of a non-linear system. So we have linear systems and then non-linear systems. So a non-linear system. So can you do you know about weather? So can you predict weather?
We can't predict, but we can just enunciate the
Statistical model.
Yeah, builder. Yeah. So weather is a good example of a chaotic system, and simple systems like these can be used to study non-linear theory.
Caught my attention is the word you use, both deterministic and chaotic. In the same sentence.
Yes.
So I'm trying to understand what you mean by deterministic chaos.
Yes. So it's because you cannot. So why the chaos term comes is that you cannot simply represent them as simple sine or cosine equations. But then why is it still deterministic is because they still have an underlying mathematical equation. So a small change in the initial condition can give you two completely different motions.
What is the end goal of this? You kind of, I didn't come in the start, sorry.
Yeah. So the end goal is that this system is highly sensitive to the initial conditions. So a small change can give you a completely different trajectory. And this can be used to study chaotic systems, nonlinear systems, and it can also be used to benchmark control algorithms. So this is a simpler way to benchmark, like say you have a new control algorithm for a small robot car or something, and you have a new control algorithm. So instead of directly applying it over there, you can apply it on a simple simulation like this, or you can apply it on a simple system like this, that we know its dynamics, that has been widely studied. So a double pendulum is widely studied, and control theorists use this as their starting step to any control algorithm or any work that they are working with. Yeah.
So is that you use this Python model to?
Yes. So this.
See, this is Python.
Yeah. This.
Say LLM or
No.
model use regular traditional.
No. It's just traditional model. So I just have my dynamical equation, systems of equation, and I just run a numerical solver over it. So we have a differential equation that can describe it. So that is what I call as deterministic. So there is a simple mathematical equation behind how it changes. Yes, you can take.
If I put the arm here, it will start moving. It is rotating fast. Same setup is here. There is a motor inside. You can see through the hole. It's rotating fast, but the output is slow. This is a gearbox. Increases the torque. Reduces the velocity. So you have to choose your gearbox as that your velocity is good enough, but also the torque is good enough. This actuator uses to run robots like this at each joint. So this is a robot dog. A robot dog has a muscles to rotate his joints. A robot
like this robot dog has actuators as muscles. So that's why it's called the muscle for robots. Now you can see it is rotating. So this also has a motor to each joint has a motor and a gearbox to increase the force. So motor generates the motion and gearbox increases the force. So basically this is how it is converting electrical energy in the battery to mechanical energy of the robot. Any questions? What a This is a planetary gear set. First layer, second layer. You want to rotate? Rotate. You are able to rotate it, but it's hard, right?
What is it?
Yeah, I'll tell you. Now rotate this. Easy, right?
Yes.
It's easy, right?
More levers than harder it is.
This is very easy. This is very easy. So this is the same thing. This analogy I gave you to tell you what gearboxes are. So this is a robotic actuator. These are the muscles of the robot. So this help robot joints move. Like animals have muscles, like humans and animals have muscles. Robots have actuators. So actuators is made up of two main important parts: motor and gearbox. So motor is the part that generates motion. It converts electrical energy to mechanical energy. The gearbox is the part. So now the mechanical energy is generated. So it might be able to lift some weight, let's say 1 kg, but it is not enough. So we put a gearbox. So what gearbox does is, as you see, it increases the forces. So let's say the motor was able to lift 1 kg, this will be able to lift, let's say, 10 kg. If you add more gearbox, it will be able to lift even more weight, let's say 100 kg.
But it is becoming harder and harder.
So that is because the torque is increasing. But you can also see it becomes slower. So I'll show how. So this is a motor in working condition. It's converting electrical energy in this battery to mechanical energy in the motor. So this is similar to what is there in fans, right? In your houses you have fans. See, similar motors are used there. So you see this rotating. This is an actuator. You can see motor inside, and there is a gearbox here, similar to this. So the motor you can see is rotating faster through the holes, but the output is rotating slow. So that's the point. If you want to increase the force, you have to slow down. Okay, understood? So it can now, so if this lifts 1 kg, this can lift 14 kg, but it will also, if this is rotating by 14 degree, it will rotate only by 1 degree. So that's the trade-off.
You need more energy to rotate this.
No, same energy. So same current will lift 1 kg here, but 14 kg here. But the same current, if this moves by 14 centimeter, this will move only by 1 centimeter. Same to cars. If you have driven a car at low gears, your car can go on inclined courses, but it goes slowly. At high gears, it can move fast, but it cannot go on incline. So because in high gears it produces less force, high velocity. On low gears it produces high forces but less velocity. So the same logic is here. So now we have this actuator. So which runs the robot like so. Each joint of this robot is an actuator like this, and so dogs have muscles to move their joints. Robot dog has actuators like this.
The ones here?
So each leg has 3 here. One is inside, not shown. It has 2 areas. So each leg has 3. So total 12. 12 of these. So that similar, so it can move on various surfaces. So each joint is something like this.
How are they coordinating with each other?
Yeah, that is controlled from the program. So there is a input. So there is if, as a human, even if you close your eyes, you know where arm is, right? Because there is an internal sense neurons which tells you where your arm is. Same thing is here on the actuator. There is an encoder sensor which tells you at which position it is. So this controller is telling, this computer is telling to a given position, and how it knows it is at that position is from that sensor.
So it knows the correct position and then you send.
We tell, okay, go to this position, go to this position, and do it. Any questions?
You can also use humanoid robots also.
Yeah. Similar actuators are used in humanoids. You just need more better motors, more higher gearbox, etc. Yeah, so I'll tell you, this is
One. What's the use of this?
robot dogs. So the robots are mostly, the word robot came
Got up the coffee all sit. It's recording, that's what you
There is a 30% rate of center in cancer cells. So how this works is we use cancer cells to we use ultrasound, and ultrasound causes vibrations like what you just saw. These vibrations actually what essentially happens is these vibrations the cells can actually sense these vibrations, and it causes the activation of a pathway that causes the cell only in cancer cells. Yes? No, not yet. It's just in research phase, and our target is to actually translate it into clinical approach. We also work on stem cells, where you guys know what stem cells are. So stem cells are actually cells that can differentiate into different types of cells in our body. So what we want to do is we are using ultrasound to differentiate stem cells into bone cells. And that can be used for diseases like bone density reduction and bone fracture.
There are two neutrophils, one macrophage, one T cell, and one pathogen. You can try to guess who's who.
Pathogen is the venom.
Yeah, right. Yes, you're right.
Neutrophil
This is Mike.
Spider-Man.
This is? You're right. And this is? No, it's a T cell. Yeah, okay. And this?
You're right, perfect. Now I will explain what neutrophils do through this model. So here you can see the different strategies neutrophils follows for killing off the pathogen. Here you can see cytokines which are released when a neutrophil detects a pathogen and tries to call more neutrophils towards the infection site. Next, it releases something called ROS. These are the reactive oxygen species. These are released so the pathogen can be digested better. Next, they also do something called phagocytosis. I think you might have heard that in school. They engulf the pathogen inside their body so that they can be digested inside. Next, they do something called letosis. So like he guessed, this is a neutrophil, Spider-Man. What does Spider-Man do? He releases all these cool webs, right? So neutrophils do something similar where they release a net-like substance which is made of chromosome material and histone proteins to engulf bacteria that is bigger than the neutrophil itself. So here we have a game which represents the neutrophils in the blood which will attack the tissue site which has multiple infections. What you have to do is these two are the neutrophil balls. You have to guide them towards the tissue where there is infection and grab on all the bacteria within 1 minute. Do you think you can do it? You can give it a try.
You start the timer.
Yes, I will start the timer.
Yeah.
Yes. Almost there. Try to drag it slowly.
Make sure
you know where the magnet is, right? Yeah. Yeah. Okay.
Nice. Slowly.
Slowly. Yes. Nice. Okay. Almost there. Almost there. You can use both the balls if you'd like. Maybe you can use this ball for this. Drag it slowly. Yeah. Yeah, almost there, almost there. Yes. Nice. You can go there. Yes. 3 more to go. 10 more seconds left. Come on, come on. Nice, nice. 1 more. Almost done, almost there. Time up.
Nice, nice.
Very good try, very good try. You guys can all get one sticker.
Yeah, I will get.
What is the rest? What is the rest?
Thank you.
Welcome. Did everyone get a sticker?
Yeah. No? Okay. So basically, our lab is an immunoengineering lab. So we work on immune cells. So this has. Can you just shift it? Thank you. So this is the Marvel, you know, right? Yeah. Exactly. So we have interpreted the different WBCs and a pathogen in the form of these Marvel characters. For example, this is Venom. What do you think? What does it represent?
The
infection. Yeah, the pathogen. Yeah. Perfect. Yes. So this is macrophage, which is a mighty Batman. So macrophages are also very big. So it is represented by this Batman. And this is the Spider-Man basically, which is a neutrophil. Okay, so I will explain what this neutrophil does. For example, there is an infection in your body. There is an infection. Okay, thank you. There is an infection in your body. So what happens is, for example, there is a pathogen. It sends this pathogen.
Apparently they lack this architecture compared to the normal cells. Where the normal cells are so good, they can form very nice blood vessels, and the gap is so less. Where compared to the tumor, the lack of this architecture such that there is a gap in between the cells. So we have to take the advantage of that. We have to make the formations such that these formations are bigger than the gap between the normal cells and smaller than the gap between the cells which are near to the tumor. So that these can pass through this and this will not pass through the normal cells, which reduces the toxicity to the normal cells, to the normal tissue. It is a treatment and everyone can actually do it. So something will accumulate here and the particles which are moved into the tumor, they can come back. You can ask the question, but the blood flow is very high, it will not come back and the tumor environment is so sticky. So that these particles will stick to the sense and more efficient.
What kind of drugs are is it already existing or is it?
So people are already screened some of the drugs. Still people are doing screening tests and so our lab basically take the drug which is already existing in the market and reformulate
So that it can
vary in the sense.
So if blood cells can't come from weight can't come from cats have lost weight, why can't it come?
Because of the blood flow is so big, it will be retained here and one more thing is tumor environment is so sticky. So the these will be attached to the cells. Okay. So that's the reason these will not come back. That's the reason we have
Dogs or humans, you use muscles to move your joints. In robots, you use these actuators. So you can see this is a motor. This is an actuator. So this is an actuator. This is a motor moving at some speed. You can see it is moving at some speed from the holes. There is a gearbox very similar to this motor gearbox, and this is the output. You put your leg here. Okay. Now, what happens is, you can see this is moving faster than this. So this is a 14 gear ratio. What this means is, this can lift 1 kg of weight, motors. The output can lift 14 kg. Okay. But the problem is, or not the problem, this has to happen, that if this rotates by 14 degrees, this will only rotate by 1 degree. So this is basically like car. So your car at lower gear 1 can go on the inclined plane, but it cannot move faster. But at high gears, it cannot go on the inclined plane, but it can go faster. So same thing. So if you want to move fast, be here. If you want to move slow but have larger force, move here. So this actuator are used in all the robot joints. So basically these are the muscles of the robot. The joints of the robots are run by this. Now I'll show. So this is a robot dog. So each leg has 3 joints.
Now using this kind of mechanism.
Yeah. So this actuator or this, so in animals or in dogs you have muscles to move. So if animal has to do this, it will use its muscles, right? I'm using my muscles right now. But robot uses this actuator. So you can see each joint is being rotated. So each leg has three joints, or 3 actuators. Okay. And overall it has 4 legs. So 12 in total. These are 12 actuators. So that's how this actuator are the muscles of robots. Any questions?
Thanks. Fine.
It is it gives you a completely different behavior.
So say for example, I start this initial condition. I started like this. So you will have that it rotates, twists, turns, but you won't see this in a simple pendulum system. So here I have a simple simulation for this. So anyone you want to try placing here you can drag and drop, place this. So wherever you want, here this also you can change. Okay, so you can press play. So you see this is the initial condition, and you can see that it's not a simple to and fro motion. You have complicated twisting and turning and so on. Now say I have another system. Can you try to match these two exactly here? Like to your best. Okay, are you guys happy? This is good? Okay, you can try playing. Press play. So initially, though it is a very small trajectory that is happening, initially you will see that it exactly follows the trajectory. But then slowly you will see that it moves away. Even though we saw that the initial conditions were quite good, quite overlapping, but then with time, you will see that you get a completely different trajectory, a small change. That is because our initial conditions that we just placed wasn't 100% exactly the same. There was a small difference. But then also there is this difference. So how we are solving it is that there is a numerical that's an argument to
Only tell us the structure. They don't tell anything about whether convergence will happen or not. For that, we designed something called Laplacian matrix, which is just degree minus adjacency.
Convergence to the consensus?
Yeah.
So by consensus, you're basically it will result in leader election?
No. Some same position they need to reach.
Sorry?
Same position they need to reach. Right.
Okay.
So this is a Laplacian matrix, and if you look closely, you will see that if you multiply this matrix with some constant vector, then you will always have 0 in the end. So you can model all the consensus dynamics using the equation called x dot is equal to minus Lx, which tells you what is the rate of convergence. So Laplacian matrix will always have a constant vector in its null space. That means you will always get to a position where rate of change will be 0 eventually. So that means you will eventually reach a vector in which all the positions are same. So that is why you need Laplacian matrix.
This is like a swarm intelligence, like
yeah.
trying to navigate on its own.
So consensus can mean different things in different ways. Suppose sometimes you want to reach some position, but sometimes you want to maintain some formation. That is also one consensus. Or maybe in opinion dynamics, suppose you want to reach to some similar opinion based on the interaction of human beings. So how can you model that using this? Now the interesting part is, suppose you have some agents, but someone introduces their own agent, which is not covered by the dynamics of consensus which you want to have. So what that agent will do, that will eventually disturb the eigenvalues of your whole Laplacian matrix, and that will determine where the agents eventually converge to. But this is like passive system.
Yeah, wait, over. Yeah. Okay, so I'll start the time. You have to reach in 60 seconds is still not the lowest scope. So you have to go 3, 2, 1, go.
Having it. Columbus.
So we'll consider that due to wire. Yeah, you use stuff.
It was not working.
What?
I was pressing left, it wasn't working.
See, it's working now?
But when I pressed it, it wasn't working.
You have to press little right. ಇಲ್ಲ ಅಲ್ಲಿ ಇದು ಮಾಡ್ತಾರೆ ಲೈವ್ ನೇರ ಸರ್
ರೆಕಾರ್ಡ್ ಮಾಡ್ರಿ ಏನ್ರಿ ನೀವು
ಸರಿ ಸರ್ ಸರಿ
ಯಾವ ಮೂಡಲ್ಲಿ ಇದ್ದೀರಾ ಇಷ್ಟು ಹೋಯ್ತಾ ನೀವು ಅವ್ರು ಕೊಡಿ ರೋಹಿತ್ ಕೊಡಿ
ಮೇನ್
ನಾವು ಅದೇ ಬೋರ್ಡ್ ಮುಂದೆ ಆ ಬಸ್ ಕಂಡಕ್ಟರ್ ಬೋರ್ಡ್ ಇದ್ದಾರೆ ಅದೇ
ಅಲ್ಲಿದ್ದೇವೆ ನಿಮ್ಮ
ಬರೋ
From the fundus camera we will collect those data, and from that data we will give to our software, and that software will diagnose it, means it will give some report like you have this normal eye or it is like some kind of disease, like 3 type of disease I have shown.
Practically have you implemented it in any hospital?
Means it is in like we are developing it, like we have to fine tune it with some images from, so we are collecting those images also. Means we are planning to
The database.
yeah, we are fine tuning the model actually. After that we will
collaborating with different hospitals across the country like AIIMS, Delhi, AIIMS Raipur and all. And our current existing model, what we have, we are fine tuning it using the real data on the field.
Affordable medical facility.
Yes.
Yeah, it is.
So the early detection and referral. Yes. Certain cases which would have otherwise been missed by the doctors or the medical people, that we are trying to take it and refer so that we can prevent blindness. I wanted to show the images of the in these 3 conditions.
This is like a report generation, automatic report generation from.
Not really. Report will be generated based on the fundus image of the retina. So you can first take the image of the retina through the fundus camera and then put it to the AI model.
Even without symptoms, you can, based on those factors, you can tell whether you're at a risk or not. Once she knows whether she's at a high risk or not, if she's at a high risk, she will go and see the doctor. So the act suggests that she has to go and see a doctor. So once she goes and see a doctor, then they will do mammography and so on. So that is why Nirvaya AI comes in and helps the doctors and radiologists based on the images tell whether the patient has to do a biopsy immediately or she can wait for 6 months or 1 year. So in this way, we are trying to reduce the time in the diagnosis and start the treatment early if the women is at risk.
This is the Windshield AI app. So it's quite user friendly and the advantages it's there in
Different languages.
Yes. So once we accept the conditions and all, after that the questionnaire works. And the app, of course, the dashboard is a little different. It's something shady, the dashboard looks like this. So general questions are asked, regarding their lifestyle, their income. All these are general questions. After that comes breast examination questions. In this, those who haven't undergone the breast examination, they have the option to see the video. So it's actually a compulsion. They have to watch the video, and on that basis, they have to do self-diagnosis. So that's what I am. So we
it will be very close, as close as possible to the expert level or the psychiatrist levels. So then that information is used by the Asha worker, and they will refer a person to the tertiary healthcare center like a hospital or district mental health hospital or a primary healthcare center. So they will get help. So right now the diagnosis and the screening itself in India is very low. So people themselves don't know that they probably have a mental health disorder.
This is the app.
Yes, yes.
It's effective,
So we've started the pilot right now. And we're targeting that we should have 99% effectiveness. That's the plan.
So you have both streams, IT and science impact.
Yes, of course. Yes. So there is a research component. So typically what happens in research in academic institutions, research stays inside the lab. But we are trying to translate this research into the public domain by doing all this. Take it to the outreach, increase the outreach. Yes.
आप लोग डिटेक्ट कैसे करते हैं पेंडुलम?
So हमारा
This is a lesion. I'll take a photo of this. And you can see this will tell suspicious. So this will inform the frontline worker that this case is suspicious, and the screen will come something like this. And the patient is asked to refer to a dentist. India has around 1/3 of the world's burden for liver cancer, and most of the cases are detected in later stage. And around 8 out of 10 are detected at the later stage, which is quite a huge number. So we are trying to reverse this, and we want to detect around 8 in an early stage, and we have built an app so that we can do that. And this app can be used by a frontline worker like Asha and ANM. We collect some demographic data
Adjacency.
So electric energy gets converted to rotation, just like your fans. This is the same motor, just smaller. Motor produces motion. So by motion, maybe you will be able to lift 1 kg. But now you want to lift more. Like when you want to lift 10 kg. And what you do is you put a gearbox. Now with this, the same amount of electricity, you can lift large weights, maybe 10 kg. Let's say you want to lift 100 kg.
will have been added to this. Okay? So these are the two parts of the muscle. We call this muscles of the robot. Because humans and animals have muscles. Robots do not have muscles. Robots have these.
We just got the stars on the hand. We didn't do the card.
Good job, one guess. Oh, you didn't play the game.
So this is a magnetic resonance MRI where we have a very strong magnet, and this magnet will give different signal outside our body, and we can see any. We can see our organ.
It basically depends on the density of the water that is present in each of the organs or the part of the tissue. For example, bones have very high density, right? And muscles have comparatively lower. With that difference in the water percentage, yeah, we can get the good image in MRI. You can. This is a MRI fruit scanner that we have made. Okay. You want to go with kiwi? Okay, no, you don't need to take the plate. Just take the fruit and place it on the patient table. You see? These are the seeds.
These all are the seeds.
You can move it.
This is how it is taking the image slice by slice, and it is giving a 3D image.
This is the first slice. Yes.
And then again coming back.
So the same one is applied for humans.
Yes. Yeah. You can try different vegetable also.
Wait a minute. Hi, you can place it now.
This is like smaller.
version.
Yes. Yeah, this is a smaller version. This is similar. Same principle as MRI. Yeah. So basically, MRI is a magnetic resonance image where you have a very strong magnet. So our Earth is also a magnetic field, but that is very less. That is nano Tesla. But MRI we use Tesla, like 3 Tesla, 7 Tesla. So this is a very strong magnetic field. So whenever we are going for a human imaging, any organ imaging for brain or something, so we can get different signal from bones, from muscles, from water, depending on the water content inside. So the same setup we have made here, and you can scan the fruit how we scan human organ in the real MRI. So you can choose any one of them. Okay, you are going to garlic.
If cancer cell increases, then game is over. So you have to choose wisely what treatment you give to the system. The cancer cell increases or decreases. Now you can check with different time steps what happened. Cancer cells start increasing. If you reset it, then the whole system started from scratch. Now the treatment budget is so you can check with different time steps.
All the body organs. This is normal. Cells.
What is?
Okay. So this is there in all the body organs, and this is very normal. Our cells needed to, move around the body parts generally. So we've simulated that. And this is the basement membrane, and this is the tumor core, as you can see. So we have 16 tumor cells in our tumor core, and the red ones is the epithelial tumor cell. So these don't migrate more. Okay, these are very they just remain. They just slowly migrate. And yellow ones is the mesenchymal cells. So these migrate a lot. And when a epithelial cell want to have more nourishing environment, like in a tumor cell want to have a more nourishing environment, it moves to a different site, a secondary site for more nourishing environment. So what happens is the red cell converts to a yellow cell. But the caveat here is that not all cells will change, and in what pattern will they change. Okay, so I'll run the simulation and you have to observe and tell me what is happening. Okay. So you can see that the cells are degrading the matrix and they're invading, right? So you have to observe and tell me what is happening.
It's the same.
to ensure that it is thermoregulated, and that becomes okay. So you use that thermoregulation from the body to ensure that the structure stays in shape. So according to application, we can change the kind of biomaterials that we use. For example, if you need something for a bone implant, or say you have a major fracture and you need the bones to grow over there, you can have biodegradable materials that will self-resorb into the body after, like, say 3 to 6 months. But if you have cases wherein you are providing support to an occluded artery, say like a stent during a blocked coronary artery or something like that, in those cases, you need biomaterials that are like one surgery and you're done. You don't have to keep doing the surgery again and again. And also, you should not have cases where the thing degrades and it leads to another stent being used. So, depending on the application, we have lots of biomaterials with which we work on, and that's the kind of work that goes on. So this is another sort of a biomaterial which we have. So these are based on gelatin, methacrylate, and alginine. So all of these are gelatin substances. Very soft layer for like flexible tissues. So these are
stiff substrates. So in soft substrates, you tend to have like less migratory behavior. Cells are more stationary and these rounded morphology. But as the cell goes towards stiffer surfaces, this promotes a migratory behavior where you see a change in the morphology of the cells. You get these protrusions and formation of lamellipodia. So this whole process is called durotaxis. How forces affect cell movement.
So what is practical use cases of them like?
Sorry?
What are the practical use cases of this technology?
So one is wound healing. So that explains wound healing when you have like in our skin when you have a cut and that has to heal. Cells have to move back. So you need cell movement over there. But you also have cancer metastasis where you have the tumor, but then they spread. So cells move there.
No, not that kind of division, movement. Like one cell is over here, right? It moves in the
You want to know? Yes. So we are looking at how epithelial cells move. And we're trying to understand how forces around the cells affect this movement. So one thing is looking at how stiff substrates of the layer on which cells are, how stiff they are, and how that stiffness affects movement. So this is a process called durotaxis, where people have seen that when cells are on softer substrates, this basically promotes a less stationary cell. So cells are not very
Sir. We are collecting stickers. You'll get a prize.
I saw you send me a
Then they put this side so people don't start their
That's what talking about.
Whatever I know, I know.
This is where do we put this?
Wherever there's a baby cycling there is a limit.
And there is an active
restriction because we saw.
You are not keeping at the junctions.
You can try out
Keep it at the minor junctions, not at the major.
You want to buy 4 pieces with combined to make up a set. You have to make up a set out of max. You get it correct when you
This is a one way. Like going is not allowed, coming is allowed.
So, generally we expect to go in one direction, so is allowed. So other direction, if you are going, then you will be fined or you can be punished.
We are mentioning the direction
Try some harder ones.
I am not getting the other position.
You want to mention there will be a signal. You want to mention before the signal there will be a signal. You want to reduce the speed. That's the reason we are using signal in front of the code. And you want to cross the road. What sign you are using? What sign they are putting? Pedestrian cross.
That's the reason we are mentioning the pedestrian crossing. This should be, what is this sign? Signal. If you place it here, this is wrong. If you place it here, this is right. Why? Yes, you are coming from this direction. No, you are coming from this direction. This signal for these peoples. If you put it here, this will show you can go for straight, you can go for right. If you put it here, for example, if you put it here, it's not, for example, if you bring the vehicles below, it's not visible. Signage is not visible. That's the reason. Signal is not visible. That's the reason they want to. Understood?
Because we have a meaning
Hydraulics are linear tools, but rotational. You have to convert this into linear into rotational motion. You have to have mechanism for it. So that increases a lot of weight. So the best hydraulic humanoid robots are minimum 100 kgs, but the best rotatory motor humanoids are as less heavy as 30 kgs.
Are you pushing motors? I was about to ask you this. These motors which you are showing over here, these are radial motors. Are you looking for axial motor development or how?
We are
because so that you get the higher torque weight.
Yeah, that I know, but we don't want to jump directly into very difficult problem. We want to take a simpler problem and try to solve. Simpler problem is we take a given type of motor, we try to find these. So first, I think first step is to identify the most crucial parameter. People have done research which have found out that this radius of the motor is directly proportional to the
square of quadratic proportional to it.
Yeah, so the thing is not right. I forgot that it is directly proportional.
No, it's a square proportional, R square.
Okay, so the thing is this: basically the diameter is high, torque is high, but the torques are high, then it also gets heated up. So it's a trade-off problem which you have to know. So we want to make simple. We want to make simple
Your data set more diverse and as well as that overfitting of machine learning model would happen. But this requires great segmentation by training models. How you capture now you see. For example, you take up my photo. Where that photo goes now?
It will goes to the app and it will say the diagnosis.
Okay. That photo somewhere it has to be saved, right?
Yeah.
That photo, if you take that one and you can do this some analysis and you take out the outliers and your data set will become more rich and your predictions will become more realistic. So that photos where you are capturing right now or
yeah,
you are not storing it anymore?
We are storing the photos, but we are not using.
They need the storage device. No. That's what I'm trying to say. That it's capturing or not.
We are capturing the photo.
They have already this
So we are continuously building better model, and we are in a phase of building another model which is continuously being trained with what you're. I'm understanding what you're trying to explain, that we should utilize the photo that we capture, and we are capturing it, we are storing it, and we are training out.
So right now
we are developing different
data set only.
But that is a different version.
Yeah, only this one.
70K. This 70K data set will be collected from?
Collected from, these are from the different patients from different parts of India.
30K is a retrospective data.
No, you can encourage, right? But you can't force them. You can tell them that you need care, but you can't force them. Right. So the idea is to be able to diagnose, catch it early, so that it doesn't go to a stage where, so it's early screening basically. So we don't want a person to reach a stage where they need emergency help. Right? That's the idea. Where are you guys from? Here in Bangalore?
We're integrated with Approximations.
Okay, very insightful questions. Thank you. We are doing the data set. We are collecting the data set from ground up.
Is it like you tie up with hospitals and
yes? So we have tie-ups with the district health officials. So we are going door to door. So Sushma is our public health specialist. She is running the pilot in the field. So she trains the Asha workers, and then they go door to door. We also have tie-ups with Osmania Medical College, NIMHANS, and Manushanti, multiple mental health chains.
I mean, are they okay to give the data because it's really sensitive? And
So we take informed consent. So everything has to go through a proper protocol here. So we have our ethical committee which governs what we are collecting, how we are collecting, and only with the sign-off from the ethical committee. Ethical committee is also eminent personalities from the mental health space, and it's a very strict guideline given by the Indian Council of Medical Research. So we are following all the protocols.
Is that control is so suppose if attack happens, then how can we change the metrics so that we don't get influenced by the attack but we reach our desired goal? Yeah. So we model that. So this Shamshad?
neutrophil will start to lose. Idea is that so idea is that if you don't take risks, you will get stuck in a local equilibrium and may not get a global equilibrium. This concept can be applied in AI training as well, where if you don't train for long enough time, you don't have a good data set, you'll be stuck in a local equilibrium and have a bad model as opposed to a global equilibrium or a better model. Yeah, that's the concept. So this one, not this one.
See up front.
I didn't know that.
I want to try this give one sprint.
Aeronautics Singo.
It's the close up for 3 double balloon.
There's another left.
How did we go to That's why I don't know when to see first the ground actually. I think they will understand. Drug delivery lab and all.
Just telling him about glycination in the morning. They might see this.
Okay. We'll call them.
Yes. Wait, it will not be going.
So we have a set of MRI images. These are all called structural MRI images. What does it represent? Which bone? Which part of the body is it?
Spine.
Spinal cord, neck spine. Neck spine. Cervical spine.
You can place it inside slowly.
What is this? Which part of the leg? Yeah, you're pointing it correctly. It's the knee, correct.
So all these are seated inside the kidney.
So what is this? What do you think this is?
So you can see the
We all have that.
whatever
Brain.
Yes. Without even
What is this? This way.
So how the original MRI
Which part? Which part? Go down and what do we have in the below the stomach area?
slice by slice, and you can get a whole meal or any other organ or any other system.
Below that, you see this, right? This is the spinal cord. What is below that? How do we walk? What do we walk with?
There are slides.
Below the, before the legs, what do we have? Hips, 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 and the urinary bladder right here. This is also the brain with eyes.
Which one you want?
Different view. This is also an easy one. What is it? Yes. 2 kidneys on either side and a liver. This black structure is the liver. I think we showed all. This is the which bone? Which bone? Shoulder bone. Good job. I can do an experiment here if you want.
Okay, and the whole thing you have to place it inside. Very slowly. And you have to see here. So you can see all the slices, right? So these you can see the seeds also. These are the seeds inside the fruit. So these are the 2D slices. So if you combine all the 2D slices together, you get the 3D image. That is the same thing that happens for human MRI also. You get the slices of some organ or something, and then when you put it back together, you get the 3D image of the entire organ. So and then the doctor can analyze if you have any problem there or not. You want to try some other?
You want to try some other fruit or vegetable?
Take it out.
Okay, strawberry.
Here it is. See?
I'm really sorry.
Yeah, let's see. And what side, how it looks.
This is actually a model, but we have made it using Arduino and Python.
Python is what is inside this camera?
This is a proximity sensor.
Proximity sensor.
Yeah. Yes.
Okay. So what is this?
This is strawberry. So
Is it showing the image?
yes. If you move,
Real image.
Proximity sensor.
Demonstration available in YouTube.
yes.
It is available in YouTube.
Whatever you're doing,
Should be available. I think we are doing the podcast for the whole institute.
Yellow is more invading. So, but the caveat here is that not all red cells would convert to yellow, right? And in what pattern do they convert is also important. So, what we're trying to understand is that will this I'll run the simulation and then you'll get to know what is even happening. So you can see that the cells are degrading the matrix and they're invading faster. So I'll ask you about observations now. Like, what did you guys observe in this simulation from the initial point to now?
It started spreading.
Exactly, it started spreading and red cells.
Recently we use it for patient applications. For example, certain patients, for example, these kind of patients, we come with the cornea. We can create a 3D polymer of the chip using the cornea, and then we can create lens out of this. And these lens can be given to the patient, and they will be comparison, and this will replicate how the cornea actually works. So that's what we try to do. This is one of the material which we have. This is a gelatin. This is what we exactly try to do in the 3D printing. So this cross links at the.
He's showing one such material which we use.
So you can see that it formed like a 3D structure.
Yes, sure.
You can see. It formed it's like a viscous liquid, but it formed like a 3D structure. So these kind of structure which will exactly replicate in the 3D printing setup, and then we will create structures. For example, certain patient like this particular curvature of the cornea. But that is what we replicate. We will get the CAD model from that, and then we will design it, and then we will print it in the 3D printing setup. For that we will do it. At the same time, we will use those cells kind of cells for the cell culture testing. For example, every drugs which we consume cannot be tested in humans. It has to be tested in animals for these kind of in vitro cells. So we'll try to mimic these kind of things in the in vitro
You have all the other cells, which is the follower cells. So now it pulls the entire sheet of cells and the moon gets covered. Now, but this area where these cells were initially is now empty. So for that, this rearranged cells multiply among themselves and it forms a sheet of cells. And so this is the process of food printing, and when you observe it, it appears like this. Do you guys have any questions? So this is the setup for
Yeah, that's what overall process.
So these balls are?
These balls are the nano formulations. So if you take the drug normally, drugs are like some sub-nanometer range. So those will easily pass through the things. That's the reason the chemotherapy have a lot of side effects because of the loss of hair and the body will loss will be there because these drugs are can pass through this. So you have to make some platform or some package that can carry this drug inside and it can be delivered into that. Okay, so kind of polymers or liposomal or some compartment to carry these in the range of 100 to 700 or 1 micron range and goes into the tumor rather than diffusing. So there it comes some engineering to make it proper size and.
But usually tumor removed or is it just integrated within the body?
So you can do the surgery to remove it. So if there is no surgery, if you don't want to do surgery, this EPR effect and making the formation for a sustained release will be the better option without surgery.
Chemotherapy also.
So we are from drug delivery lab. So we are from drug delivery lab. So this is EPR model, enhanced permeability and retention. So we'll discuss something. So there is a city, there's a population which grows very rapidly. So government wants to do one thing that let's build one building so that people can stay, people can stay. So government sanctioned some 100 crores for that. But the vendor who was there, he built that building in a month or 2 months. That's what happened. And there is a lot of defects afterwards, right? So that's what happened in the tumor also. So tumor is like uncontrolled growth of the cells, and this is not there. Suppose there is a whole tumor tissue, so they need nutrients and the oxygen. These are tightly packed, so there is no proper diffusion of the nutrition and the oxygen. So they want to increase this blood vessel into the tumor tissue so that they can get a proper nutrients and the oxygen to expand their tumor. So the thing is they lack this. They lack this building of this whole blood vessel. So compared to the normal cells, they have a specific particular architecture that so specific that they don't have gaps. Where compared to the tumor, they lack that architecture to build these vessels. So there is a gap between the cells. So this is the advantage for tumor also because the blood will go, nutrition will go, oxygen will go. But this is a disadvantage for us. But we have to make it advantageous. Such that you make a particle, you make a drug particle, which is the bigger in the size than this drug.
It's just a game.
You can start.
You can play this.
So, we are the immunoengineering lab where we work on immune cells, engineer them to elicit response according to what we want them to elicit. So, this is a model of a neutrophil where you can see the different strategies they have to kill off pathogens. So first what they do is they detect a pathogen and they release cytokines and ROS. These are chemicals that are harmful to the pathogen and also call more neutrophils to the site of infection. They also do something called phagocytosis where they basically engulf the pathogen towards their cell body so that it can be degraded. And they also do something called netosis. So netosis is the process where they release a net-like substance made of chromosome material and histone proteins, which can be used to capture very large pathogens. So we have designed a game where you can see what exactly happens in our body. So this is our blood vessel and this is the site of infection. Here you can find different bacteria where the neutrophils can come and capture all of them and phagocytose. So you have to do all of this in 1 minute. That's the game. So maybe you can give it a try now.
Okay, we will not give out stickers anymore, okay?
What are the responses?
These are reactive oxygen species. So these are harmful chemicals to the bacteria.
ಅಲ್ಲಿ ಹೋಗಿ ಎಲ್ಲ ತುಂಬ ಜಾಸ್ತಿನೇ ಇರುತ್ತೆ ಇದು ಆ ಥರ
ಕೀರ್ತನ್ ಕೀರ್ತನ್
We have a demonstration.
बात कर रहा था
This left, right,
I mean, robotics also is drawing a lot of crowd. I think because of this games and all.
You don't know, so what?
What will happen is they will use it, themselves the Asha workers will use it, and they will get the inference is what we call it, whether it's a high risk or a low risk. If they are found high risk, then they are asked to go and contact a primary healthcare center or a district mental health facility.
How humanly are the questions during mental need to be asked very humanly, right?
So right now it's a very rigid questionnaire which is socially, it's already validated in the community setting in India. So we are using those questionnaires. But we want to move on where, like you said, we will adapt these questionnaires and not ask these questions directly. So it will be through a chatbot kind of a thing where we are indirectly trying to get a response to a specific item in a questionnaire. So it could be, are you sleeping badly? So that's one of the questions. So that could be asked in multiple different ways. So we will build that eventually.
Then what are those mental diseases referred to as? Like, what is it?
So we are looking at common mental health disorders like depression, anxiety, substance abuse. Substance abuse could be alcohol, smoking, and cognitive impairment if a person is older than 60 years of age. We've just started our pilot, so we have rolled it out in Kolar right now. We are looking at pan-India. So we have built the app and Kannada.
You know what? It's like it can't be expressed using classical physics.
Right, that's one way to go. And the most
predicted.
It can't be predicted. That's one thing.
So, chaotic system isn't actually a random system, basically. So the thing is, a small change in the initial state will make a totally different behavior of the whole system happening. So that's what happens here also. So, I mean, if you give it a motion, this looks good and all, but let's say the main thing that we want to show is here. So let me reset it. So can you guys give an initial state to it? Like you can click and drag on it to change the position where it is. Okay, so let me do it. So I'll just give an initial position to it and let's go. So this follows some trajectory which is like really hard to actually put into an equation, a proper format. Okay, so let this be one trajectory. Let's pause it now. The second thing, I want someone from here. Someone come down. Just try to, keep it in the same initial states as possible, as much as you can. Like how it was before. How it was before. Like you got the points, right, to mark it. You can use that. Try to keep it in the initial position as much as possible. Done? Okay. Yeah. Are you fine with this? Everyone is fine with this? Are you play it? Yeah. So the first thing that you will see is it is starting to go in a same motion. But as you can see, after some point of time, it starts to deviate. After some
value will determine the speed of the convergence. So if you have very fully connected graph, very dense graph, you will have very less zeros in this value. Value will be higher. So that determines the speed of convergence. Now the interesting case is when you have suppose disconnected graphs. Basically, if some element of graph is not able to communicate to other graph, you will not reach one consensus, but you will reach consensus on the basis of number of groups. Now suppose if you introduce a malicious agent which is not governed by the dynamics of Laplacian. So what will happen is you have no control over the system, only Laplacian is playing a role. So these agents will converge, but eventually their convergence point will be influenced by the malicious agent. They will eventually try to reach their goal. Now if you want to prevent that, you can introduce a control matrix in this system. And
Better than 100. Yeah, but if you put a red, there's a risk of getting 0 as well. Probability. So this entire branch is called game theory, and we study how simple games to complex games like this are played and what is the best strategy to play in each of them. So if you want, you can try a slightly different version. You want to play
game theory? What is it?
So it's a branch in mathematics, computer science and all. Mostly probability, yes. So I mean it's very widely used in economics, computer science, math and all. So it kind of models situations in the real life where you'll have to make some strategic decisions. You'll have to choose some strategy to interact with someone else. So instead of 2 cards, you might have infinite, or not infinite, 100 cards. So what would be the best card to play? And even you can model real world situations. In fact, even traffic signals for that example are modeled using game theory. They check when you need to, let's say you are the police officer there, and which light do you want to put as green and which red, so that everyone is happy or something. So all these real world situations can be modeled using game theory and studied to a very
No, we can't be sure.
Forward, right, left.
No, right.
Start.
You should not touch that ball.
Take a right turn. Yes. Yes, take left turn. थोड़ा सा straight. Now take a left.
You have touched.
You have touched many times. What is this name?
Like it has a microcontroller named as ESP32. By that we can control it by one through one session. Okay, ready.
ESP32.
Here you get more force 1 day. Now here you can get more things. So both cases might not be done. It means add a layer of more. This particular concept cost is the force multiplied by the motion and the velocity. Initial state. You get initial state. Let it run for some time. Now the goal is to keep it in the exact same position after it runs, such that this trajectory or the path it follows should be easy. Okay, click next. Yeah, try to click those.
Okay, so now what? This is a different game. Now what do you think the best thing is? Before one you told it was black. Now what do you think is the best?
You have a red and a black, you have a red and a black. I have already done that.
ನಮ್ಗೆ ಬರೋಣ ಆಕೆ ಮಾಡೋಣ ನಮ್ದೇನಾ ಬೇರೆ ಬರ್ತದೆ ಅಲ್ಲಿ ಇದೆ ಅದಕ್ಕೆ
Suppose you have an environment in which many agents are by agent so suppose they are interacting with each other. Sometimes the scenario is like all the agents want to each other. Very apart, but actually they want to each other. Social dynamics of they have different but based on the interactions with time you all will be the same. This is consensus how you can model this is like this. Suppose you have 4 agents, for example. You can formulate this as a graph in which each robot is and all the connections are. So you can mathematically how you can represent this is in a matrix which tells you the connectivity.
4 by 5, 4 by 4.
Based on number of agents. N agents, N by N. Right? So each row will represent one robot or one agent. And suppose robot 1 is interacting with only second and then that value will be other values will be. So this eventually will be for all the agents and this will represent the connectivity of the robot. Right? But this does not tell you anything about whether there is convergence. For that you can design another matrices. From this matrix design something. This will tell you how many robots each robot is connected. For that you can just sum the column
Some based on matrix.
If you subtract adjacency from it, you subtract adjacency from the matrix. So what happens is Laplacian matrix there is something called eigenvalue, which is a quality of that eigenvalue can determine the convergence so this matrix will eventually ensure that you converge towards. But how fast that will be determined by this so there are many cases in which each agent is connected to each other. And in that case, they will transmit information very fast. So they will converge motion very fast. But if suppose some agent is not connected to any agent, if it is incompletely sparsely connected, that convergence will be very slow because information is not accessible to each agent. So you can have another scenario in which you will not reach one position, but you will get groups in which you will get two clusters because each group is not connected. Now the interesting case is suppose you have some agents and some enemies has their own agent, right? So what will happen? These agents want to reach some value, but this agent will make sure that they reach their value. So you don't have any control over that. But how
how you can introduce control is using another matrix. You can introduce a matrix, you can consider B matrix, and design inputs in such a way that you control the behavior of these agents so that they reach their goal but they are not influenced by the malicious. So, real world example will be suppose if Indian Army sends their robots and they want to reach some location. But enemy countries, robots are also there. So how can we control the behavior of other hard agents so that they don't get detected and controlled by malicious? So this is like cyber attack.
So basically these are agents itself. I mean, it cannot be global agents because one can communicate with each other easily.
But you can model the scenario using this one.
The human example you can take in the case of social media. In social media, we have a lot of number of people, they interact with each other. So those interactions you can model using these matrices. And there your problem of interest would be like converting to a certain opinion. So everyone has their own opinion. But through the interactions, they will form different groups. So each group will converge to one set of opinion. So you can use this kind of analysis to study the behavior of these social networks.
Yeah, so adding to the social network, so sometimes what happens is suppose government needs to introduce some policies. So how do they ensure that that policy reaches people very efficiently and how do they determine the transmission? So or if even election is coming, so some parties may introduce their malicious agents which will influence the opinions of others.
That bots kind of thing which actually publish some malicious news about the other person. That would also
they will make the connectivity to a lot of nodes and even drive it.
They convert the social media with all the malicious.
This one is like
many things. Main problem is but mathematically you
just give those humans
matrix theory and control theory. So matrix control theory uses matrix theory.
You develop a software.
You can then
this
take
one is
it
for
to
just to show the simulation. So, like some kind of gaming kind of situation, not gaming, this is a guessing situation, in which I will show you the behavior of the malicious agent.
In any scenario, you have interacting agents.
And then in the next one, you can guess what the malicious agents are. So first I will show you a simple simulation. In this, the agents are nothing but the points on a 2D coordinate system. So first they ask because the purpose is to show how the connectivity affects the convergence. So if you have a very dense graph means one node is connected to every other node, then the information exchange will be very faster and the consensus will happen very fast. So suppose I select such a situation. So see, in this case, the convergence happens very fast. In this case, since the state is nothing but the point on a 2D coordinate system, all reach to one point, then the error reduced to 0 in almost maybe 5 to 10 seconds. Now suppose if I make the graph a bit sparser. So right now I have 30% sparsity in the graph, so not all the nodes are connected to every other node. In that case, the consensus will be very slow. So it will take a lot of time to reach to the 0 error. Why is this important? In real life situations, these interactions means maybe some communication you have to get. So you have limited number of resources. Like in case of robots, you won't be able to design communications between every robot. So if you have resources limited, how can you decide which robots to connect so that the consensus reaches what is desired? So this is one design. Coming soon.